When you've completed this lesson, you should be able to read and interpret exponential graphs on both linear and semi-logarithmic scales. You'll be able to graph exponential functions on those semilog scales and read and interpret the very important type of graph called polar graphs. And you'll be able to graph with those polar coordinates and convert back and forth between rectangular and polar coordinates. You're going to encounter a wide range of data in your photonics career, relationships that are linear, exponential, and polar. And the best way to look at that data often is on a graph. Now, sometimes linear graphs work, but sometimes logarithmic scales are a better way to present the data, and sometimes polar charts are the best. And technicians need to be able to draw, read, and interpret all of those different kinds of graphs. So for example, if you're examining the fall off in light intensity from a source, since the intensity varies with both the distance and the angular position around that source, a polar graph of r versus theta is the most helpful kind of graph to use in that situation. But before we look to that, let's look at an example scenario that a photonics technician might solve. You may have a fiber optic cable that's carrying light whose performance varies with the wavelength of the light. Notice here we've got a graph of the varying losses that occur at the various wavelengths, but the scaling on the vertical axis is not like you've seen before. This is called a semilog scaling. We'll learn more about that in this module. Looking at that graph, can you tell what is the power loss per kilometer of this cable for light around 800 nanometers or 1550 nanometers? And at what wavelength does that cable present the highest loss in power per kilometer? And what is the value of that loss? Well, let's spend a few minutes reviewing important types of graphs and look a little bit closer at this logarithmic scaling of the vertical axis. When we graph exponential functions, they are different from linear functions. They don't have a constant slope. Let's consider a common electrical relationship which does have an exponential relationship. Here we have the voltage of a capacitor that is charging, or in this case, discharging through a resistor. V is the voltage across that capacitor that we're going to measure. V0 is the battery voltage that was initially used to charge that capacitor. R is the resistance in ohms. C is the capacitance value in farads. And T is the time since the charging, or in this case, discharging, began. Let's look at that exponential function. So if we have a 10-volt battery charging a 250 microfarad capacitor and is being slowly discharged through a 2 kilo ohm resistor when we close the switch, then the capacitor's voltage can be measured over time, as we've shown here. At time 0, it exactly equals the battery voltage, and so the ratio of V over V0 is 1. But then as it begins to discharge, its ratio begins to drop down closer and closer to 0. Let's consider a graph of these ordered pairs. You can see that they drops very rapidly at the start and then sort of flattens out and more slowly approaches 0. Well, that's an interesting process, and that process is very important. It's called exponential decay. You will encounter things like this often in your photonics career. These values approach 0 in this case asymptotically. That is, they get closer and closer to 0 but never quite get there. If we were to zoom in on that portion of the graph on the tail end there, we would see that it's not yet to 0. And if we kept on going past 2 seconds to 4 seconds, it would never quite reach 0. Well, the rate at which it decreases depends on the values of R and C. And if you look in our formula, in the exponent we have T divided by RC. So if we have a large RC value, then the curve is going to be much flatter than it is right now. If we have a smaller RC value, that curve will be much steeper. So R and C seem to have a very important effect on the shape of our exponential decay graph. That product, RC, is known as the time constant, or tau, the Greek letter tau. T-A-U is the way it's spelled. And we can rewrite the discharge equation then using that tau, that product of R and C. So V over V0 is equal to E raised to the minus T over tau power. That time constant is a very important parameter in exponential decay problems, just as slope, we learned, is important in linear functions. Now let's look at logarithmic functions, which are somewhat related to exponential. The intensity level of a sound that we measure is modeled by a logarithmic function. So perhaps you've heard about sound levels in decibels. Well, this is the formula that we use to calculate the decibels is equal to 10 times the log base 10 of the ratio of the intensity we measure in watts per meter squared divided by the threshold of hearing, a very, very low intensity level of 1 times 10 to the minus 12 watts per meter squared. So for some measurements of some various sound intensities, we can produce a table, just like here, where we have the intensity that's measured, the I values, and the IL, the intensity level values. And you can see at the hearing threshold, the IL value is equal to the log base 10 of 1 times 10 to the minus 12 divided by the threshold, which is 1 times 10 to the minus 12. So that's a log of 1, which happens to be 0. And then as we get louder and louder and louder, the intensity levels increase. So we can try to graph these values on a linear x and y axis. We can graph from 0, 0.2, 0.4, 0.6, 0.8 up to 1, our highest intensity, up versus our intensity levels, which is those log values. And we see that they're almost all of them are right up against the axis. They're all very small until we get to the last value. That's not a very useful graph to interpret. The problem is that most of those x values are so small, they're all 10 to the minus 10, 10 to the minus 5, 10 to the minus 4, that they're all right down there hugging the y-axis. Even if we dropped the highest value and just started with the highest one was 10 to the minus 4, they would still all be right up against the y-axis. So we need a way to be able to somehow spread those out. We need a different kind of scale on the x-axis. The solution to that is to recall how the logarithmic function took very large numbers and returned the power of 10. Since the I values are so small, we could plot the log base 10 of I instead and reduce the effect of the large and very small values on the same graph. So here we have an even easier solution. Instead of taking the log, we'll just use logs on here, the powers of 10. Instead of 1, 2, 3, 4, 5, we'll use the powers of 10. So we'll start with the biggest value is 1, and then the next one we'll go down to 1/100th, or in this case 10 to the minus 2, and then 1 to the 10,000th, 10 to the minus 4, and then 1, 10 to the minus 6, 10 to the minus 8, 10 to the minus 10, 10 to the minus 12, and 10 to the minus 14. So you'll see that our horizontal axis is actually logarithmic in nature. It's not linear. And when we do that, we get a straight line relationship almost. One of the values departed a little bit, but our exponential relationship or our logarithmic relationships will appear as a straight line. Let's look at another example of a semilog graph. Look at the table of values here. These are clearly a power relationship, right? This is 10 to the 0 power, 10 to the 1 power, 10 to the 2 power, 10 to the 3 power, 10 to the 4th power, 10 to the 5 power, and 10 to the 6th power for x's of 1, 2, 3, 4, 5, 6, 7. So clearly this is a power series here and not a linear relationship. So you know that if we graph that on a linear graph, things would look very awkward. Let's look at those two graphs and compare them. There's what happens on a linear graph. All those, if we try to scale our y-axis so we can get that largest value in there of 1 million, then all of the first 5, even almost 6 values are essentially along a straight line, and they really aren't telling us a whole lot on that graph. That's the problem with a linear graph and exponential kinds of functions. So we can now look at a different kind of graph, as we saw in the previous example, a semilog graph that has the scale on one axis is no longer linear, but is now logarithmic. So we have the powers of 10 here instead. And now when we graph our data, you'll see that it is in fact a straight line. And now we can do things like interpolate and so on between those points, and it's actually meaningful. So the semilog graph is much easier to interpret. We call this semilog because only one of the axes is logarithmic. There are cases you'll encounter where both the x-axis and the y-axis are both logarithmically scaled, and that would be called a log-log graph paper. And when you only have one of them that is logarithmic, either the x or the y-axis, then you would call it semilog graph. Okay, so let's turn our attention to a different kind of graph, a polar graph that represents data on polar coordinate system. You've seen the Cartesian coordinate system. That's a rectangular grid of x and y ordered pairs where we plot the x value and the y value and determine the location of a point. There's another important coordinate system called the polar coordinate system, which basically looks like a big dartboard. If you'll notice, in the center is where we start, and if we move out, we'll have 1 unit or 2 units or 3 units. This will tell us how far out the r value should be for our first coordinate of our ordered pair. The second coordinate in our ordered pair is the angle, and that specifies how far around the circle we'll plot our point from some sort of zero reference line. Usually we'll take a line that stops right there about at the 3 o'clock position as our reference for 0, but you can find polar graphs that will use due north as 0, for example, or any other angle as a reference point. With this coordinate system, we can locate any r and theta value by just simply going out from the center, a distance r, and going around the circle, some angle theta. You can orient and label a polar chart in many ways, but as I said, we will always start with 0 being at the horizontal 3 o'clock position there. And we'll use, in this case, a scale of 1, 2, 3, 4, 5 for our r values. You can just as easily use 10, 20, 30, 40, 50, or 2, 4, 6, 8, 10, or whatever you would like, just as you can on a Cartesian coordinate system. Some polar coordinates, let's look at the graph of those. Here's r and theta equals 3 and 0. So we didn't move up at all on the angle value. We went out r equals 3. How about r equals 4 and a theta equals 45? Well, so we go out to the 4 position on the scale and go around 45 degrees. Or 2 and 150 degrees. So we can go all the way around to the other side and get coordinates over there that are plotted. How about 4.5 and 230 degrees? So you see, you don't have to fall right on the ring, just like you can on a linear coordinate system. You can go in between the lines, and we've done that here with 4.5 and 230 degrees. Or we can get really strange results like r equals a square root of 14 and negative 71 degrees. How are we going to handle that? Well, negative 71 is going backwards, or we can also just compare that to 360, and that will be the same as 289 degrees, and we can evaluate the square root of 14 to get 3.74, so that tells us how far out from the center we have to go. Or how about 5 and 480 degrees? So 480, that's more than 360, so we have to go around more than once to get over to, well, really we just end up stopping at 120, because 480, it'll be the same as 360 plus 120. Now in real life, we're seldom going to encounter angles that are greater than 180 degrees, so we're not going to deal with those anymore in this module. You're often going to be given a rectangular XY pair, but you need to convert it to a polar R theta pair. So how do we do that? Well, let's look at this a little closer. In polar coordinates, the r value indicates the distance from the origin. So let's consider the xy point 3 and 4. Well, how far is that from the origin? Well, when you plotted that, you probably should have been reminded of a right triangle that has a leg of 3 and a leg of 4. And you know how to find the distance from the origin now. That's just the hypotenuse of that right triangle. So that's the same as the Pythagorean theorem can tell us that r squared is equal to 3 squared plus 4 squared, or in this case, r is equal to the square root of 9 plus 16, which is equal to 5. And you'll recognize that we've chosen as our example a Pythagorean triple, 3, 4, 5, which we could have done without even using the formula. But that is the value for r. In general, for any x and y then, we have that r is equal to the square root of x squared plus y squared. To find the angle theta, we can again use our right triangle that we learned about in trigonometry, where we have the angle theta is for that coordinate is related to the angle that has the opposite side of 4 and the adjacent side of 3. So that probably clues you in right away that that's related to the tangent of that angle. And we can take the tangent then is equal to the opposite over the adjacent, or in this case, y over x, y divided by x. So in this case, that'd be 4 divided by 3, which is 4/3, or we'll just round it off to 1.33. And the inverse tangent of both sides will allow us to tell us what the angle for that is, and that'll come out to about 53.1 degrees. So we can say that the xy coordinate 3, 4 is equivalent to the r theta coordinate of 5 and 53.1 degrees. In general then, for any xy, we can convert to polar coordinates by using r is equal to the square root of x squared plus y squared, and theta is equal to the tangent inverse of y divided by x. We have to caution you that be careful using that inverse tangent function outside of points that lie in quadrant 1. If you'll recall, in our geometry and graphing units, we talked about this as being quadrant 1. This is where all the x and y values are positive. Over here, we'll have negative x values and positive y values. Over here, in quadrant 3, we'll have negative x and negative y values. And over here, we'll have negative y and positive x values. Now, as you use the tangent function, if you take 3 divided by 4 and take the inverse tangent, we got 53.1 degrees. If we were down here and we had negative 3 and negative 4, and we took the tangent of negative 3 divided by negative 4, we would also have 1.33, and theta would also come out on the calculator as 53.1 degrees. That's not 53.1 degrees though, is it? So the moral of the story is you're going to have to be very careful when using that inverse tangent function outside of quadrant 1. All right, now suppose we have an r and a theta value and we'd like to convert it to rectangular coordinates. So if we've got some data point out here that's some distance r from the origin and up some angle theta, how can we find the x and y value for that coordinate? Well, again, we'll notice that right triangle with the opposite and the adjacent sides and theta. Well, we know that opposite is really the y value for that coordinate, and the adjacent is the x coordinate. So let's look at the adjacent side. We know that there's a ratio called the cosine ratio, which is the adjacent side divided by the hypotenuse length. The hypotenuse of our triangle in this case is r, and the adjacent is our x value that we're looking for. So we can set up this equation and solve for x. But we know what x over 13 equals. It's the cosine of 22.62. We can put that into our calculator and calculate 13 times the cosine of 22.62 will equal 12. So our x value in this case is 12. Similarly, on the y coordinate, we have the sine ratio, which is the opposite over the hypotenuse, or in this case, y divided by 13, our r value. And we can calculate the sine of 22.62 and multiply that times r value and get 5. So now we know that the r theta value at 13 and 22.62 degrees is equivalent to the xy coordinate 12 and 5. And in general, we have that x equals r cosine theta and y is equal to r sine theta. Let's practice doing some of that converting, and there we'll show you the summary of all of the conversion formulas that we've just discovered. We'll convert r theta of 7 square roots of 2 at 315 degrees to x, y. So we just simply apply the formulas that we have above, that x is going to equal r cosine theta. So that would be 7 square roots of 2 times the cosine of that angle, and that'll calculate out to 7. The y value is equal to r sine of the angle, which is 7 square roots of 2 times sine of 315 degrees, and that would be negative 7. So r theta is equivalent to xy of 7 and negative 7. Now let's convert xy of 3 and 5 to r theta, to polar coordinates. So we have x equals 3 and y equals 5, which we can substitute into our formula for r is equal to the square root of 3 squared plus 5 squared, and that evaluates to 5.8. Similarly, theta is equal to the inverse tangent of y over x, which is the inverse tangent of 5/3, which will come out to about 59.0 degrees. So we have our xy point is equivalent to, the polar coordinates, 5.8 at 59.0 degrees. Now we're ready to look a little bit at that opening scenario where we had that graph on the Semilog graph scale. So what is the power loss per kilometer of this cable at 800 nanometers? Let's notice the logarithmic scaling on the vertical axis so that we know how to read that y-axis. We notice that we'll have 3 decades. The first decade's tick marks correspond to 0.1, 0.2, 0.3, 0.4, 0.5, up to 1.0. The second decade's tick marks correspond to 1, 2, 3, 4, 5, and then jumps up to 10. And you can see that the next decade would be 10, 20, 30, 40, 50, up to 100, and so on. So now we're ready to read that graph. Just like you do any graph, you find 800 nanometers on the x-axis and go over to the y, and you'll see that we're just above that second tick mark, which we know means 2. So we're going to estimate about 2.2 decibels per kilometer loss at 800 nanometers. At 1550 nanometers, we come up and come over, and now we're much lower on the graph scale, and we're at 0.22 decibels per kilometer. We're about 1/10 of the loss at that shorter wavelength. So there's a big difference, a factor of 10 difference between those two numbers, even though they all fit on the same graph. Now, at what wavelength does the cable present the highest loss per kilometer? And what is the value of that loss? Well, the highest loss is going to be at the peak of that absorption, where most of the signal apparently is absorbed and lost. And that occurs, if it can come down to the x-axis, at about 1,380 nanometers, somewhere around, a little bit less than 1,400. And at what value is that loss? How much is lost at that point? We have to come over to the y-axis like we did before. And so we come over, and that's somewhere between 10 and 20 on the scale. So we'll estimate that it's about 15 decibels per kilometer. So you notice that reading a semilog scale is much different than reading a linear scale. And you'll take some practice to do that, but I'm sure that you'll get really good at it as you recognize what the tick marks stand for. So now we're ready to tackle some of the practice exercises in this unit. So let's look at the data from a capacitor in an electric circuit that's discharging, just like the one we saw in the examples. And we're going to graph that data on a semilog graph, making the y-axis logarithmic. What scale should we use for the x-axis? Well, the x-axis will be time, and so we'll just use a linear scale divisions running from 0 out to at least 2.0, and divisions of about 0.2 should do very nicely. And what about the scale for the y-axis? Well, here's where we need to make a logarithmic scale, right? Log scales start at some power of 10 and then increment up to the next decade So our smallest decade will probably start at about 0.01 or 10 to the minus 2 because that's where our lowest values are. And our highest values need to get all the way up to 1.0 or 10 to the 0 power. So we're going to have to span our logarithmic scale from 10 to the minus 2 through 10 to the minus 1 and up to 10 to the 0 power. And here we have our graph. So we've started our y scale down at 0.01, and then we go up to 0.1 and then to 1.0. And we plotted our data as it's discharging down, and you notice that it is a straight line and not that exponential curve that we saw in the earlier example. It was a gradual curve that sloped down. And there's the tick marks, if you'll notice that they are 0.01, 0.02, 0.03, 0.04, 0.05, and so on. Notice how they get closer and closer together as we get closer to the next decade, and then they spread out again. So here we'll have 0.2, 0.3, 0.4, 0.5, and then they get closer together again as we get closer to the end of that decade and start the next one. That is very characteristic of logarithmic scales, and so you'll learn to recognize that right away when you see a scale that gets all scrunched up as it gets closer to the end of the decade. That's a good sign that you're looking at a logarithmically scaled graph. We call this a semilog scale because one of the axes is logarithmic and the other is linear. You will encounter sometimes where both the x and the y-axis are logarithmic. In that case, you don't call it semilog, but you call it log paper. Now let's look at the sound intensity, IL, in decibels using this relationship. You may have heard about so many decibels of sound intensity. This equation provides us with those values. 10 times the log of the intensity measurement divided by the threshold value, I sub 0, as we saw in the text. So let's calculate the IL values for ratios of 1, 10, 20, 30, and 100. Substitute those ratio values and use your calculator. So 10 times the log of 1 is 0. That's because the log of 1 is 0, so 10 times 0 is 0. 10 times the log of 10 is 10, because the log of 10, base 10, is going to be 1 times 10 is 10. Those were easy, weren't they? Now this one's not so easy. You're going to have to use your calculator for that. The log of 20 is about 1.3, and when you multiply that times 10, it becomes 13. The log of 30, and the log of 40, and so on. We could go on. You can go on and finish that data, and here's what your table will look like when you're done. And now we're asked to graph this table of values on linear axes. What scale should we use for our x-axis for the I over I0 ratio? Well, we were ranging from 1 to 100. So we could use a linear scale from 0 to 100, going in increments of 20, for example. For our y-axis, we have to go from 0 to 20. So we'll use a linear scale with divisions of about 5. 0, 5, 10, so on, out to at least 20. And here's what our graph might look like then. Our x-axis and our y-axis. And you can see this is kind of like an exponential curve, and this is asymptotically approaching some limit. Now let's graph those same values on a semilog axis using a logarithmic scale on the x-axis. The x-axis is, of course, the ratios of the I to I0 values. What scale should we use for that? Well, we need to start with the 10 to the 0 power, get 1, and we're going to, as be our smallest value. Then our second decade will start at 10, or 10 to the 1, and needs to end at 10 to the 2 in order to get the value of 100 in there. So most of our data is going to be plotted in the second decade, as you can see. And what about the scale for the y-axis? Well, we'll just use the same as before, between 0 and 20 in steps of 5. So now we've got our logarithmic scale on the bottom here, And you'll notice this characteristic compressing of the grid lines as we get closer and closer to the end of the decade. And our values in this case are not a curve, but a straight line, which is indicative of a logarithmic or an exponential relationship between x and y. And here's, for reference purposes, those are the tick marks, could be labeled 2, 3, 4, 5, and 20, 30, 40, 50 in this case. And typically you don't label the ones between 5 and 10 or 50 and 100 because they get closer and closer together, and that's really hard to get those numbers in there. All right, now let's look at an example of a polar relationship, coordinates in the polar coordinate system. We have measurements of light intensity that are taken at various distances and angle positions from a light source. As the illustration in the text shows, you have a light source that's up against a wall, and you're going to measure light all around at angles of 0, 30, 60, 90, right out in front of that light source, and then around to the other side over to 180 at different distances from the source, at 2 centimeters away, 4 centimeters away, 6, 8, and 10 centimeters away. And we're asked to graph the locations of our measurements, okay, at 2, 6, and 10 centimeters on a polar coordinate system. This is simply going to show you where you stood to make your measurements, or where you placed the sensor to make your measurements. So for now, we're going to be looking at the actual positions where the measurements were made, not the measurement values. So we're going to position our angles 0 degrees at 3 o'clock and 90 degrees up at 12 o'clock, just like we saw in the examples in the text. And our R values are going to range from 0 to 10 centimeters, and so we will scale our radial axes from 0 to 10. And so here we'll plot all 5 sets of polar location data rather than just the 2, 6, and 10 centimeters that we were asked to do, because it's pretty easy to do with our graphing software that we have to produce this. And so here you'll see is a legend or the key that shows you what colors correspond to which distances. At 2 centimeters, it was real close to the source, which is right here at the center. And we measured at 0 degrees, at 30 degrees, 60 degrees, at 90 degrees, 120, 150, and 180, all at 2 centimeters away from the source. Then we also measured at 4 centimeters away at these locations, at these angles. We measured at 6 centimeters away, and we measured at 8 centimeters away. And lastly, we measured at 10 centimeters away. Just as we would connect dots with lines on a Cartesian coordinate system, we can connect the dots with smooth curves on a polar coordinate system. Now let's look at probably a little bit more standard way of using a polar chart, and that would be to graph the intensity. And it's probably a lot more interesting in this case because we see that our intensity values are not the same as we go around at different angles. Polar charts are very commonly used in optics, and radio, medicine, and acoustics, and so forth. All these other fields of study which are very useful to look at angular dependence of measurements. So we're going to graph the fraction of our light intensity versus the angle theta. And we can compare those graphs at various distances r. Don't confuse the r in this case with the notation of r and theta. So we're going to use the fraction of our light intensity graph to show as the radial coordinate. And here's what the graph would look like. Look at our legend, and we see that the blue dots correspond to a 2 centimeter measurement. At 2 centimeters, we had a very high fractional source of 0.25. We measured 1/4 of the intensity of the light right there, right next to the source, and it's way out here. And if we step out just a little bit, 2 centimeters away, there's a big reduction in the light intensity. And then 6, 8, and 10 are even smaller. In addition to the relation between the close distance and the farther away distances, you'll notice that it's not uniform. There's a little bit greater intensity that's evident right out in front at 90 degrees than there is off to the sides. So you can see a little bit of a forward favoring of our light source here. Perhaps the filament of the light bulb, for example, was facing 90 degrees in this case. That also was evident at the 4 centimeter distance. We had greater intensity out at 90 degrees than we did on either side of the light. So now, what do you notice about the intensities as they relate to angle and distance? Well, since the intensities are relatively constant at each distance, let's average them over all the angles. So we'll add another column to our table, and we'll look at a rectangular plot on a Cartesian coordinate system of the fraction of the light intensity, the average in this case, versus the distance from the source. And we see a nice smooth curve that looks like it's exponentially decaying, doesn't it? This is actually what you would call an inverse square law in action here. And you've probably heard of that before, that the light intensity falls off in proportion to the inverse square of the distance from the source. Now, in exercise 4 asks you to do some practice conversions from polar to rectangular coordinates. So let's convert 17 at 81 degrees to rectangular coordinates. Well, as you saw in example 4, you'll use the relationships x equals r cosine theta and y is equal to r sine theta. So we'll substitute our values for r and theta into our expression, 17 cosine of 81 degrees, and evaluate that to be 2.66. And if y is equal to r sine theta, then that would be 17 times the sine of 81 degrees, which would be 16.79. Now, it's always a good idea to check that out with a sketch. And so we'll make a quick sketch of our point that's out at 17 units out and 81 degrees up. And sure enough, it looks like the x value should be a fairly small number, less than 4. Probably 2.66 is about right. And the y value is up there. Well, it's almost going to be 17, so 16.79 is about right. So we're confident that we've probably done our conversion correctly. And indeed, that is equivalent to xy of 2.66 and 16.79. Now let's go the other way. Let's convert a rectangular coordinate to polar coordinates. We're given 32 and 9 for x and y. And we'll use the other set of conversion equations from example 4. That will be r is equal to the square root of the sum of the squares, in this case 32 squared plus 9 squared, and we'll have the result is 33.24. Similarly, theta is equal to the inverse tangent of 9 divided by 32, will be y over x, and that will evaluate out to 15.7 degrees. And once again, let's look at a sketch quickly just to see whether that looks like it's right. If we go over 32 and up 9, that produces a dot that's out there, and it looks like it's going to be, the r value is probably going to be about 33, right? It's going to be a little longer than 32 because that's the longest side in that right triangle. That makes sense. And looks like we're up a kind of a small angle, which is about 15 or 16 degrees. We'll buy that. So we're confident that we've done our calculation correctly. And r theta is in fact 33.24 and 15.7 degrees. All right, and that concludes our treatment of special graphs in Module 11. I know that you're going to have a lot of confidence now to go on and use these skills as well as all the skills that you've learned in this course and in your photonics career. Maybe we'll see you again. Bye-bye.